Okay, so today's, today, let's just start with the usual stuff. Have your sound muted, video on. The video off permissions list has been updated. Thanks, I'm already seeing chats. Thank you, Clarissa, for letting me know about your video. Yeah, you guys are used to the whole process now. Just let me know if you can't have your video on, and I'm gonna periodically throughout the class just remind everyone to have their video on. The students who are on this list have their video off permissions updated so that basically you're permitted to have your video off. And then log on to Google Classroom and complete the do now. The do now today is like pretty, I mean, it's easy in a sense. It's just one that you kind of have to, you just think about, just like a conceptual question, and it deals with the topic that we're dealing with today. So yeah, take a couple minutes to do the do now. Good morning, everyone who's just coming in. How you doing, Hobby? How you doing, Naima? Marche? Glad I can see everyone. Awesome, awesome. So yeah, everyone can get started on the do now. The do now, honestly, today you could probably finish in literally like 1 minute. So pretty easy, just like a kind of a thinking question. So if you finish the do now early today, you can kind of relax. I'm just waiting for the other students to roll in. How you doing, Michaela? How you doing today? Everyone who's just coming in, standard stuff. If your sound muted, video on, the video off permissions has been updated here. Remember, if you are consistently going to have your video off, just fill out the request form and then log on to Google Classroom and complete the do now. Complete the do now. Hi, Kalia. How's everyone doing? Yep, the usual stuff. Just make sure your sound muted, video on, start the do now. I'm gonna pull up what I see for that. And then once I get some people turning in the do now, I will quickly go over some updates just with our assignments and stuff like that. Cool, so I've gotten some responses already. Thanks, Brianna, thanks, Emily, thank you, Kalia, for completing the do now. Hi, Daniel, hi, Brianna. Thanks everyone for everyone who's completed the do now so far. The do now today, again, is not really a difficult question, just more one that's supposed to get people thinking. Hi, Mubarak, hi, Jamal. Cool, so for everyone rolling in, people are working on the do now. The usual, have your sound muted, video on. I'll say, so for everyone who's trickling in late, try to start coming to class like on time, because we are losing a couple minutes at the beginning of class, and I'm just waiting on students right now. So on Friday, if we can be better about being here right at 9 a.m. when class starts, that'd be great. But anyway, beyond that, I'm going to start talking about the other points. So afterwards, after you complete the do now, get out your notebooks. reminder that the homework 1 packet video tutorial has been uploaded to the YouTube. I sent out an email regarding that, so everyone should have gotten that email. The video is going to be very helpful, I think, in terms of everyone completing the packet correctly. So it's definitely worth everyone to check out. Like I said before, yesterday, I think you can literally like take out the packet, pull up the video, and like for any of the problems that you have issues with, just like find the corresponding problem in the video where I work through it and then kind of figure it out. So I think that could be very helpful. And then the next point is that the homework packet 1 deadline has been pushed back 1 day. So it's been pushed back 24 hours to Friday at 11:59 p.m. Pushed back 1 day. However, I would recommend everyone just try to finish it on Thursday so you don't have to worry about it on Friday. And also, I'm probably going to be assigning like a bit more homework over this weekend. So like, it'd be nice to have a break for everyone, you know, so you're not like turning something in on Friday and then immediately getting another assignment to start working on. So yes, I would recommend for everyone to turn it in tonight, but the deadline has been pushed back to Friday. Everyone? And then, so I'm still waiting on students to trickle in. So let's also do the morning wake up question for everyone who wants to. And the question today's kind of an interesting morning wake up that I came up with, I guess. And I'm not sure if any of you guys have heard of 6-word stories or like 6-word memoirs or like just kind of like impactful 6-word messages. But if you can come up with anything interesting, I'd be curious. I think this can be like kind of difficult, so I definitely don't expect everyone to come up with something. But I think the most famous one was this one that I heard. I'll write it down. A 6-word story. It was for sale. For sale. Baby shoes. Never worn. And I think my 6th grade teacher told me this one, and I like still remember it just because I feel like it's stuck in my head. And obviously it's just like 6 words, but obviously it's like pretty impactful. For sale, baby shoes, never worn, and you can infer a lot of stuff from that. And I don't know, I just really like that concept, how you can say 6 words, but like convey so much meaning from that. So if anyone has anything interesting for a 6-word story, it doesn't have to be this impactful, obviously, just whatever you'd like, you can share it. Mubarak shared the spontaneous year of 2020. Yeah, that's great. Yeah. I don't know, this year's obviously been crazy. And I don't know, I think your story like rolls off the tongue really nicely, which is really important. Marche, do you want to come off mute? Did you want to share something?
Yeah.
Yeah, go for it.
Gender reveal, California fire, nice job. Yes.
Interesting. Gender reveal, California fire, nice job. Do you want to share what that means exactly? Or
so the whole California fire was like over a gender reveal, right? That's what they're saying. And then I'm saying nice job because like look what you started.
Oh, interesting. Okay, I did not know the background context for that, but thank you for sharing. I didn't know the background for the California fires, but yeah. Okay, how you doing, John? Ashley, do you want to share?
I would say coronavirus dropout. Life and
Oh, wait, sorry. Oh, okay, go ahead.
yeah, that's what I said. Life and downhill after that.
Gotcha. Okay, thank you for sharing. Awesome. How you doing, Jay? Okay, so thanks for everyone for sharing. I got all right, cool. So getting some more students now. For everyone who's just trickling in, try to complete the do now as soon as you can. But we're going to move on to a topic today. So again, I'll get everyone 1 minute now to set up their notes. And today we are going to be tackling intermediate value theorem. Again, per usual, just have your name, date, however else you want to set up your notes. I'll give 1 minute. Okay, maybe 20 more seconds to figure out your notebook page. Awesome. Okay, so now we're going to move on today to our topic again, which is intermediate value theorem. And I would like people to take the next 20 seconds or so just to share out your name in the chat if you have any thoughts about the do now. So the do now again is if your oven is at 250 degrees and you turn it off, is there ever an instant when the oven temperature is 170 degrees exactly, basically? And is it possible for your oven to cool the room temperature without ever like touching 170 degrees? So I have one volunteer from Root Charles. Do you want to come off mute and provide your thoughts?
Okay, I said there is a possibility because like ovens don't like cool like linearly, like what I said in my thing, it like cools gradually. So like there's a possibility that it can go from like 250 degrees to like 90 degrees and then down to 0. Like it doesn't just like go down a certain like exact amount. It just cools by itself, essentially.
Okay. I would ask you then, so when it goes to from like 250 to like 90, let's say, is there ever like even a split second where it's at 170? Like when it's those temperatures when it's in between 250 and 90? Like how does it jump from 250 to 90? Or does it just like go down to 90 really fast?
I think it just like it drops down like slowly but like quickly at the same time because it doesn't seem like it's dropping down by as much. Like for example, it could be like 250, 190, 170, then like 150, and then like it keeps dropping down at like an exponential rate.
Okay. Okay. Thank you for sharing. How about Mubarak?
I was gonna respond to the second half of that, and it was like,
Gotcha. Yeah, go for it.
I don't know. It's like if you're like 25 years old, I bet like at one point you were like 15, I guess. So eventually it would hit 170 if it's coming down from 250. I don't know.
Yeah, yeah. So that is kind of the thought process. That is the right thought process that we're going for here. So in terms of answering this question, is it possible for your oven to cool to room temperature without ever being 170 degrees? So is it possible to go from 250 to like, let's say 70 degrees, right? Without just like skipping over 170? And the answer is no. So no, like the oven at some point must be every temperature between 250 and 70. So this isn't super important for you to write down. It's more of just like the thought process. So if you don't have this exact thing down in your notes, it's not the most important. So I'm not going to give time for everyone to write this down really quick. But the idea is that when the oven's cooling down from 250 to 70, Ruchal, you brought up that it might cool very quickly. And that is a great point. Like it's possible, like for some, like we could throw ice in it or something that makes the oven cool extremely quickly. So it like goes from 250 and goes very quickly down to like 100 and then, you know, but the thing is at some point, even if it's very quick, at some instant, like even if it's a microsecond, it's gonna have to be at 170 degrees. And that's kind of similar to the concept we're gonna be discussing today, called intermediate value theorem. So let's look at what intermediate value theorem actually is, and let's define it. And this is the official definition of intermediate value theorem. So I'm going to explain it, and then I will give time for everyone to write it down in their notebooks. Hold 1 second. Okay. So intermediate value theorem states that a function y equals f of x that is continuous on closed interval a to b takes on every value from f of a and f of b. So I would say right here is what you have to copy down. This is kind of a in other words part. So I can explain this really quick. So a function y equals f of x, right? Let's say this is f of x over here. That is continuous from a to b. So from a is here, b is here, right? And this function is continuous, right? Remember, I don't have to pick up my pencil, so that's just our casual definition, right? So it's continuous. It takes on every value from f of a to f of b. So basically where a is, right, plug it into the function, f of a, right? Plug b into the function, f of b. If we're continuing, if I'm trying to get from this point to this point, and it's continuous, I have to touch every point that's in between here. Notice when I touch, like, you see I'm touching every point. There's a corresponding, like, y value for every time, like, I'm meeting, I can't, like, skip over this value, let's say. Like, I can't skip over it because it's continuous. I can't, like, jump over it and then keep going, if that makes sense. Like, this, I'll draw this, like, this y value, let's say there's this line, and it's continuous. I can't meet it and then, like, oh, I'm just gonna jump over it and then get to f of b. So that's really all that intermediate value theorem is stating. It's saying that on the interval from a to b, the function will take on all the intermediate values between f of a and f of b. So everything between f of a and f of b, the function must touch it at some point. So hopefully that makes sense just very roughly. I'll give everyone time to, I would say, draw this graph and then copy down this sentence at least, this first sentence. So I'm going to give everyone maybe a minute and a half to do that right now. So please begin. So maybe 20 more seconds. And again, just to reinforce this idea, I would say intermediate value theorem, like the words make it sound really confusing, but it's basically that idea, like if I'm going from, like for the oven, for example, let's say I'm heating it up, right, from 170 to 250, right? Let's say this is, like this is 170, right? This is 250 degrees. Basically, I have to at some point, right, since it's a continuous function, I have to at some point be at, or that was a bit, let's say we're going from room temperature from 70 to 250, I have to at some point touch 170. Let's say 170 is right here. I can't avoid being 170 degrees. I have to at some point be exactly 170 degrees. And I also have to at some point be 200 degrees and 220 and 90, and every value that's in between 70 and 250, I have to, the oven at some point will be that temperature. So hopefully that makes sense intuitively. Okay, cool. So now we're going to move on to an example that will illustrate intermediate value theorem for us. So the first thing that we have to remember is that it's kind of a requirement that a function of y equals f of x that is continuous. So it needs to be continuous for intermediate value theorem to apply. So let's just take a look at this function first. It's a piecewise function g of x, defined at the interval -3 to 2. I'm going to give everyone 1 minute to copy down this problem. Please start now. You can copy down the the parts if you want to, but for now, at least just this initial problem, like at least this part for now. Give everyone like 45 more seconds. And then for people who are done copying and are looking at the problem, I would like for someone to volunteer for part A, just type your name in the chat, to how we would start determining if the function is continuous over this interval. Remember, what is our definition for continuity that uses limits? If you'd like to shout out, please chat your name. I'm going to give 10 more seconds for everyone to copy down the problem. Awesome. Okay, so Tver, would you come off mute and help us determine if the function is continuous on the interval from -3 to 2?
Okay, I think we have to input -3 into the first one and get that value. I don't know, I just know that we have to figure out if the limit on both sides is equal to each other and if f of -3 and f of 2 are equal to each other. I don't know. Okay,
gotcha. Yeah, I think let's develop that point a little bit. So you're right about the limits, right? The question is, this is a piecewise function, so where are we really concerned about whether it's continuous, right? We have two functions, right? And then we have a second one, right? The second one, I'm not really sure what it looks like. I'm not really sure what either of these look like. But where are we really concerned about whether it's continuous or not? Do you have any thoughts? If not, I can move on to the next volunteer.
Wait, what was your question?
So where would we be really concerned about whether the function is continuous or not?
At -3 and 2. Between -3 and 2?
Yeah, between -3 and 2. So how about Marche, would you be able to come off mute and give us that exact point?
0.
Yeah, that's exactly right. So 0 is where we're concerned about whether these functions are continuous or not, because that's where these two pieces meet, right? So it's two pieces, and we're wondering, like, do they meet at the same point? If they meet at the same point and it's like that, then great, it's continuous. If they meet at different points, right? If it's way down here, then that's not continuous. So we're really concerned about 0, because that's where these two functions meet. -3, like, that's, we, like -3, we don't necessarily care, because we don't care about what's beyond -3, right? There could be some other random function over here that doesn't meet at -3, but we don't really care about that, because we're only concerned about the interval between -3 and 2. So what x values between -3 and 2, that's like clearly like of interest here is 0. So we're going to employ the limit definition for continuity. So the limit as x approaches 0 for g of x must be equal to g of 0, right? And you touched on this to bear how the two-sided limit must equal that point. So basically the two-sided limit that we're looking at is going to have to equal each other. So I'm going to elaborate on that a bit. So I'm going to write this. Basically, this is the same limit definition. I'm just writing it out a bit further. So the limit as x approaches 0 from the left, right, must equal the limit as x approaches 0 from the right. And this must equal g of 0. So this is just the limit definition expanded. So I would like, so if we're plugging in 0 from the left, can I get a volunteer to tell us which function we would be plugging 0 into? Awesome. How about Steve? Could you come off mute, please?
Is it x squared plus 1?
Yeah, that's exactly right. So this first function, x squared plus 1. So we're going to plug 0 into here. Could you take us through the rest of the parts too, Steve? So how about from the right, which one would we plug 0 into?
1 minus x squared.
Awesome. And then how about this final part where we just plug in 0 directly?
You mean where? Oh, you mean to the right?
So it's g of 0. So if we plugged in 0 into this, yeah.
Wouldn't it be x squared plus 1? Well, 0 squared plus 1 over 1 minus 0 squared.
So it would be this first one. Yeah, awesome. Thank you for that. So basically, we're putting in 0 into g, right? So g of 0, and then we're looking at where this domain is. So 0 fits into this domain, right? Because that's where, when x is less than or equal to 0, so when it's equal to 0, then it's x squared plus 1. So we're just doing the same thing, 0 squared plus 1. We're not putting it in 1 minus x squared, right? Because that's when x is greater than 0, but not equal to. It does not say equal to. So if we write this out, 0 plus 1 is equal to 1. 1 minus 0 is equal to 1. 0 plus 1, again, is equal to 1. Awesome. So this is great. This tells us that it is continuous. This function is continuous. Basically, we're told that this piecewise function, the limit from both sides, they're equal to each other, right? So that means the limit, they both approach the same point, they're approaching the same point, and that point is equal to those limits. So that point is right there. So that tells us that it's continuous. Now, remember we did this whole thing because we're thinking about the intermediate value theorem, right? Well, actually, I'm going to give everyone 15 seconds to copy down the work here. Okay, cool. So remember we did this all for intermediate value theorem. So if a function is continuous now, and we have a closed interval of a to b, we have to remember that it takes on every value between f of a and f of b. So let's find out what f of a and f of b are. So we're going to compute the numerical values of g minus 3 of g of -3 and g of 2. So basically we're just plugging in -3 and 2. I'm going to do this really quick. So g -3, we're going to plug -3 will obviously be this equation, right? Because that's where the domain is. X is -3. So it's going to be -3 squared plus 1 is equal to -3 squared is 9 plus 1 is equal to 10, right? Now g2, which domain does that fit into? It fits into this domain, right? Because when x is less than or equal to 2, we're going to use the 1 minus x squared equation. So we're going to do 1 minus x squared. X is 2 in this case, so it'll be 2 squared. It'll be 1 minus 4 is equal to -3. So basically, we have this continuous function, right? We can think about it this way. We have a continuous function. It's continuous, right? There's no jumps or anything. And it goes from -3 to 10. Right? So it goes from -3 to 10. So what does intermediate values theorem tell us about all the middle values, all the intermediate values? Let's see for answer C. I would like for everyone to take 1 minute and think about question C. Explain if you think the graph of G must cross the x-axis. X-axis is when y equals 0. Remember that? Somewhere between -3 and 2. So 1 minute, and if you think you have an idea, you can just share your name in the chat. And -3 and 2 is our domain, remember. So it goes from -3 to 2. Again, if you have any thoughts on part C, just share out in the chat. Here's where we employ intermediate value theorem. Cool, okay. So Steve, would you be able to share out what you messaged me in chat?
I said yes, because to get from negative to positive and vice versa, you must pass through the x-axis.
Yeah, that's a really good way to think about it. So basically, remember, we're going from, well, 10 to -3, -3 to 10. So and x equals -3, right? And x equals 2. This is our domain, right? I'm drawing out a really rough graph. At -3, we're at 10. So this is where 10 is, right? At 2, we're at -3. So also -3 here. And then we know this function, basically these two dots, what's connecting them is continuous. So if we have a continuous function, how can I get from 10 to -3 without crossing this x-axis? This axis right here. How is that possible? And the answer is it's not. It's the same idea as the oven before. Like when it's cooling down, let's say I'm like cooling down from 10 to -3, right? I can't avoid being at 0. I have to be at 0 at some point to get down to -3. I can take like, I can try my best. Maybe I can go way up here and like try to come around, but oh, look here, I'm at 0. I can come way down here, like way back. But at some point, for me to get to -3, I have to cross this point here, this x-axis, which is at 0. And that's all the intermediate value theorem is saying, is that the values in between 10 and -3 here, if it's a continuous function, all of these values will be met. So there's gonna be a 8, there's gonna be a 2, there's gonna be a -1, right? If we're connected all these, they have to happen at some point. So hopefully that resonates with everyone. That's honestly, that's all intermediate value theorem is. So it's really important to like sit on this idea. So I'm going to go through it one more time, right? I'm going to go through this one more time. So we have a graph, right? And we were concerned about the interval from -3 to 2. So -3 to 2. This is the area that we're concerned about. That's all we're concerned about is between here. Now, we know that this function is continuous, whatever we're about to draw. And then at -3, it's at, we plugged in -3, right? And we got 10. So we know at -3, we're at a pretty positive, we're at 10. Cool. Now at 2, we're at -3. So not to confuse these -3s. At 2, we're at the y value of -3, right? So we're like over here. Now the question asks us, does the graph does it have to cross the x-axis somewhere between -3 and 2? So in this interval of -3 and 2, must it cross the x-axis if it's continuous? And the answer is yes, it does have to, because again, we can't avoid this x-axis. To get to this other point, we have to cross the x-axis. The x-axis is where y equals 0, right? Yeah, and it's not even just the x-axis, right? It could ask us, does it have to cross y equals 8? And the answer would be, yeah, at y equals 8. 8 is between 10 and -3, right? And every point between 10 and -3, it's going to have to cross. So at some point, like let's say we cross, oh, at this point it's 8. We can't avoid that. How about when y equals -1? Same deal. -1 is between 10 and -3. At -1, we can try to do our best, but at some point, bang, we're going to be at -1 if our function is continuous. So yes, that is the idea. And just to show that it's true, I'm going to draw what this piecewise function does look like. So the first part from 0 to -3, this is just a rough drawing because I plotted it on Desmos, but it looks like this. Right, and then from 0 to 2, it looks like this. If drawing this out helps you for visualizing this function, then you can do that. 2, it hits -3. At -3, it actually hits 10. So these are our 2 points. This is where the piecewise function exists, like where they meet, and they meet at the same point. That's why we know it's continuous. And look what happens. It crosses the x-axis, because again, from getting from this point to this point is impossible without crossing this x-axis if it's continuous. So hopefully that makes sense for everyone. Let's see. I'm actually going to now put everyone in breakout rooms, just to really clarify and solidify this idea of the intermediate value theorem. So I have the function formally defined here, and I think everyone has written down the formal definition. And then I would like for everyone to, when they're in, when you're in the breakout rooms, for everyone to like individually share like how you would explain intermediate value theorem like to someone else. Just using just casual language, how you would explain the definition of intermediate value theorem. So give me 30 seconds. I'm gonna make breakout rooms. And okay, rooms are all open right now. I would like for everyone to join and again, take turns in explaining to each other what your thoughts on intermediate value theorem are. Like how would you explain the definition? Thank you to everyone who's joining. Mubarak, Keda, Hobby, please remember to join. Keda and Hobby, are you there? Welcome back. Awesome. Okay, so everyone should be back now. Hopefully you guys had some good discussions about intermediate value theorem. Just conceptually, I think it's actually really easy to understand. I'm not going to ask people to share it right now. I'm going to run through this example problem really quickly because I think it'd be useful for us to do just a really quick example problem. So I would like for everyone to copy this problem down. I'm going to give like 20 seconds for this. And then if people aren't able to understand this problem, I am going to be posting a recording after class. So if necessary, you can consult that. So essentially, looking at this problem, right, we're given this function f of x. And we know f of x is continuous. We don't actually have to test it in this case because it's not a piecewise function. And also there's no like zeros that would make it like, it's not over x where like at x equals 0, it'd be infinite, so it wouldn't be continuous. There's no like asymptotes or anything. So f of x is continuous. So now let's move on to the intermediate value theorem part. Now on the interval from 1 to 2, we're asking if it crosses the x-axis, right? So let's plug in f of 1. When we plug in 1, we're going to get 2 times 1 cubed minus 6 times 1 plus 1, right? So this is going to be 2 minus 6 plus 1 is equal to 3. You don't have to write out all the math if you don't want. The whole idea is just, so f of 2 is equal to 2 times 2 cubed minus 6 times 2 plus 1. And this is all equal to 5. Oh, sorry, this is equal to -3. The top is equal to -3. So basically, that's all we need to know. So it's continuous from 1 to 2, and we're going from -3 to 5. Now, if we're crossing from -3 to 5, the x-axis is at 0, right? So do we have to cross 0? Is it possible to go from -3 to 5 without crossing 0? And the answer is no.
No.
Yeah, thank you for sharing. Yeah, so basically this problem, because we're showing that it's continuous and also that it's going from -3 to 5 on this interval, we know that it must cross the x-axis. So it must cross x-axis. So yeah, that is it for today. I'm gonna leave this problem up for a couple more seconds if people need to copy it down. Remember to do the exit ticket, turn in your notes, and then definitely work on the homework packet and try to get that in today. The deadline has been extended by 1 day in case you weren't here for that at the beginning. So the deadline for the homework packet was extended until tomorrow at midnight. But I would like everyone to try to complete it today. Additionally, for the homework packet, if you have not looked at the homework packet tutorial video thing, definitely take a look at that. It will be very helpful. I'm going to kind of draw this clear if you're still waiting. So we're going from -3, right, to 5. From the interval of 1 to 2. So from like over here, from 1 to 2. So like we very clearly have to cross this x-axis, right? If it's continuous, because it's going from negative to positive. We can't avoid 0. We have to cross the x-axis. If people have questions, I can stay for a few minutes after class. Sorry about rushing through this last problem, everyone. If you're still here writing down notes, sorry about that. Hopefully you can still get down useful information though. Steve, Mubarak, how you guys doing?
Good.